Hey everybody, great to see you again. Mr. Smith here. In today's slide deck, we're going to get right down to it, and I'm going to give you all of the math that you're going to need for our entire unit on light. And what's great about that is that we can be so efficient with it because you've studied almost all of this math before when we've talked about mechanical waves and we've talked about sound. So in sound, we talked about sending out a beam of sound and getting an echo, just like you would throw a baseball against a wall and catching a reflection. And your car, if you have a smart car, that's got a lot of sensors on it, is actually going to use that exact technology. So here's how it works. This car with this sensor up front, say if you're closing down a car in front of you because they've stopped suddenly, can send out continuously a beam of light energy called LiDAR, which is a version of radar that works on infrared light. And by beaming out that energy and getting it back, your car is able to do a calculation on how far the car in front is away. So it's really an echo question, right? And that means that it would use the formula D equals V times T. So we're going to give you one of those in just a second. Before we do, a couple of things I want you to write down. The speed of light is way different than the speed of sound. It's super, super fast. 300 million meters per second. 3 times 10 to the 8th meters per second. So that's true whether you're in air or whether you're in empty space, which is the thing that's special about light. It doesn't need a medium. And because the speed of light is so fast, oftentimes we'll use metric prefixes to describe the time that it takes to go someplace. So 1 millisecond, remember, is 1 times 10 to the minus 3 seconds. A microsecond is 1 times 10 to the minus 6. A nanosecond is 1 times 10 to the minus 9 seconds. So those are things you want to write down and keep handy, okay? So here's the example. Your car sends out a LiDAR signal. It gives us the wavelength of that LiDAR signal and tells us we receive a reflected pulse 3 microseconds later. If the question is how far away is the second car, by now the thing I expect you to be good at is that obviously we're thinking about the light wave just like it's a baseball. We're going to beam that ball out, bounce it off of another object, and catch it back. And what that means is that this wavelength right here, it's nice, but it's irrelevant to us. So what we really care about is getting the distance from your car to the second car in a straight line. And you should also notice that the time, 3 microseconds, is the out and back time. So what we've got here really is an echo question. So the time that we're going to zero in on is 3 microseconds, and we're going to divide that in 2 because we're going to want the time that it takes just to travel one way. So obviously that turns out to be 1.5 microseconds, and we'll put it all together right here. So D equals speed times time. The speed we just mentioned was 3 times 10 to the 8th meters per second, and the time is 1.5 microseconds, so 1.5 times 10 to the negative 6 seconds. And when we do that out, we should get 450 meters. Okay, so example number 1, D equals VT. Okay, so this next one to me is really neat. It revolves around a very simple formula that we've talked about plenty already. Velocity equals wavelength times frequency, and that's called the wave equation, right? So when we talked about sound, we noticed that pitch, what we hear as the pitch of a sound, is related to the frequency. High frequency equals high pitch. Well, the brain also interprets light in kind of a similar way, and this is where it gets really fascinating for me. So red is the first color on this spectrum that our eyes can actually discern. So if you notice, what's below red is called infrared. That means it's heat. So heat is really part of this same family that we think of as being light, just like ultraviolet, which means above violet, is part of this. In fact, everything on this entire spectrum is a form of light in some way. So they all work basically the same way that we'll talk about. They all have frequency, they all have wavelength, but it's just this narrow little band in here from about a wavelength of 400 to a wavelength of around 700 nanometers that our eyes can see and interpret as color. So the math is straightforward. They're asking us to think about this same question we did earlier, where we had the wavelength of the LiDAR given to us, and they're asking us the frequency, so we're just going to plug in. We know that the speed of light is 3 times 10 to the 8th meters per second, and we know that they gave us 1.5 millimeters, so that means I'll do the math I need to do, 1.5 times 10 to the minus 3, right? And we'll do the division, and we get that the frequency of the LiDAR signal is humongous, 2 times 10 to the 11 And just like we did with sound, the frequencies of light waves are measured in hertz. It's just that their frequencies are really insane, okay? All right, so let's go check out the next one. It's also an oldie and a goodie. So if you remember when we talked about sound, we said that if you had a loudspeaker and sound went to fill up a space, it would fill up bigger and bigger areas, and the light intensity or the sound intensity followed a formula like this: I equals P over 4 pi d squared. This formula works exactly. The only thing you have to keep track of in a problem like this one is just to read it. A light bulb uses 6 watts of electrical power and generates 5 watts of light energy. So the number that we want for P, the power, that's going to be this one. It's the light energy that actually leaves the light bulb, right, and spreads out into space. So what we're going to do is just take what they gave us and see what we get. So we'll take 5 watts of light energy coming out of our light bulb, and we have 4 pi times 3 meters. And this would be a good time for you just to pause the slide deck, plug this into your calculator and make sure you're getting it right, and come back. But what I'm going to get is 0.044 watts per square meter. So there you go. Nothing tricky or new. How do we use this in class? Well, you can use it a lot of ways if you're trying to write algebra problems. You can make people solve for distance. You can make people solve for power. But one of the things that we're going to do is a variation on this formula, and it's really a straightforward and useful thing. Let me show it to you right now. So we'll have a couple of lab experiments coming up where we're going to do a calculation just like this one. If we know the intensity of sunlight, so 1,000 watts per square meter, this is a fact, is about the intensity of sunlight that most places in the world get at noontime. So if we know that that number is what it is, and we could figure out how many square meters of area a surface had, we just have to multiply the two of those to figure out how many watts of sunlight fall on the thing, okay? So that's what we're going to do. So I know that the intensity is 1,000 watts per meter squared, and I'm going to take and convert each of these into meters to figure out area. Area is going to be 1.05 meters, so as always, physics is going to use meters, times 2.1 meters, and what I got out of this guy is 2.205 meters squared. So what I have to do is just make sure I multiply and kind of factor label. Watch it. Power equals 1,000 watts per meter squared. You can see the units lining up to cancel, right? 2.205 meters squared cancel, but the numbers don't, and we get 2205. So that's a lot of power of sun. Well, this is a really big solar panel too, and they come in all different shapes and sizes. One of the things we're going to want to do is to see how good are they at their job, and to do that, we're going to need to know a little bit about electricity. So what's cool about this unit is that we study both light, but we also start to move into electricity, and I'll show you that right now, and that's the first of our new formulas, so let's go check that out. So here's our new formula for electrical power. Power equals I times V. I'll explain the pieces. Power of electricity depends on two things. The voltage of the electricity is like the push behind the charges. So charges at 1,000 volts have a lot of motivation, and they tend to be a lot more likely to spark than charges at 120 volts would be. And this will be a thing that we actually experiment with and play with in class. It's really a lot of fun. But 120 volts is standard household voltage in the United States. So that's a number that you'll see a lot of. 0.05 amps in this question refers to what they call current. So I'm going to say just a little bit more about that. I know the letter I was the thing we used already, and it meant intensity when we were talking about light. If we're talking about electricity, it means the flow of electrons. So a big current would just be a lot of electrons flowing, just like a big current in a river would be a lot of water flowing. You've heard of volts, I think. This one you might also have heard of. Current is measured in what are called amperes or amps of current. So the formula itself is not going to be tricky. What we're going to do is just go and find the thing with amps on it. That's going to be the current, and we'll put that right there. We'll put the voltage where he belongs. We'll multiply them, and what we'll figure out is that this electrical light bulb, this LED bulb, is going to draw 6 watts of electrical power. So let me give you an example of how we're going to use this. So with a light meter, we can read how much light energy is falling on a panel. And then with devices like this one, which looks exactly like the multimeters that we have, we can measure things like the voltage and the current that come out of it. So the formula is just the formula. It's nothing tricky. Power equals current times voltage. And this is going to be the electricity that comes out of the solar panel. So 703 milliamps, you should know, is 0.703 amps. So I'll put that there and make sure I do the conversion to the standard normal unit of amps, and 11.5 volts is a standard normal unit. And when I multiply them, I get 8.1 watts. So is that a lot? Well, it depends on the size of the panel. So let me go and talk about how good the panel is, and we're going to bring up the idea of efficiency. So for electrical devices, what that looks like is just the ratio of the power we get out to the power we put in. And this is going to work for light bulbs or solar panels, whatever. Just keep track of which is which. So in a solar panel, the light that goes in is obviously solar power, and the energy that comes out is obviously the electrical power. You could also tell because the number that's smaller is always going to be on the top, because there's no device in the world that's more than 100% efficient. So you just do this fraction, multiply it by 100 to turn it into a percentage, and you're going to end up with 21.8%. So that number, 21.8%, is so good that over a lot of the United States, the wasted solar energy that just falls on people's roofs really becomes a valuable thing. So we'll talk about that plenty more in class, and I want to give you one last, not even real formula piece of math right here. This is just a reminder. A kilowatt hour is a unit of energy, and it's equal to a lot of joules. So a kilowatt hour is equal to 3.6 million joules. So it's a little conversion factor that you might want to use, but I'm going to give you an easier way to deal with it in this problem. A kilowatt hour is literally a kilowatt times an hour. So if I have a 3,000 watt solar array that's working for 6 hours, all I need to do is take and figure out that I have 3 kilowatts, right? That's 3,000 watts operating for 6 hours. And what that equals is 18 kilowatt hours of electricity. So that's the amount of electricity you might use in a day. That's the amount you might produce if you have panels. But anyway, that's it for now. So bring your questions with you to class. Great to see you, and talk to you real soon. Take care. Bye-bye.